What is the vapor phase composition? So we have studied an equation Pi that is equal to Yi into P total, where Pi is said to be the partial vapor pressure of the ith component over the solution, and Yi is said to be the mole fraction of a particular component in the vapor phase, and P total is the total vapor pressure over the solution. Then we have also written it as Yi, this is equal to Pi divided by P total, and applying Raoult's law we have also written as Pi naught into Xi divided by P total, and using these formulas we have also solved some problems based on it. After doing that, we have studied something about types of solutions. So we have studied about ideal and non-ideal solutions. We have studied the definitions of it. I told you it is very important for the board examination. We have studied about ideal and non-ideal solutions. Ideal and non-ideal solutions. We have studied about the definition of it. Studied about the definition of ideal and non-ideal solution. Then we have studied about characteristics of ideal and non-ideal solution. Then we have studied about types of non-ideal solution, types of non-ideal solution. After studying about types of non-ideal solution, we have studied differences between ideal and non-ideal solution, ideal and non-ideal solution. Then we have studied about differences between positive and negative deviating non-ideal solution. Non-ideal solutions. We also studied about the definition of positively deviating solution and negatively deviating solutions. Then we have studied about the examples for each. Examples for ideal, positively deviating and negatively deviating solutions from ideal behavior. Then we have also studied about what are the reasons for non-ideality. What are the reasons for non-ideality? What are the reasons for non-ideality? It is all about the interaction between the solute and the solvent. So we have studied these many concepts in the last class. In addition to this, we have also studied about the graph of non-ideal solutions, graph of non-ideal solutions, graph of non-ideal solutions, graph of non-ideal solutions. We have also studied about the examples of that. Then we have studied something called as azeotropes, types of azeotropes, definitions and examples, definitions and examples. So all these concepts we have studied in the previous class. After that, we have studied about what is a colligative property. After that, we have studied about what is a colligative property, definition of colligative property. After studying about the definition of colligative property, we have seen the examples for colligative properties. So it is relative lowering of vapor pressure, and we have derived some expression for this also. And the second example, what we thought was elevation in boiling point. We did not study anything about it. We have to study it today. Elevation in boiling point. And the third thing that we have studied is depression in freezing point. Depression in freezing point. And fourth thing, as an example, what we have studied is osmotic pressure. Just we have mentioned the name of that, osmotic pressure. In the last class, we have studied in detail about RLVP. So let me go ahead with RLVP. What is relative lowering of vapor pressure? We have already derived it as a glance. We need to derive that, then we have to solve the problems on that. As I told you, one problem is definite based on colligative properties. Now let me say that we are going to study what is relative lowering of vapor pressure. Relative lowering of vapor pressure. Vapor pressure. In short, we will always write it as RLVP. We'll write as RLVP. Now, as we have studied in the last class that always we are preparing a binary solution. We are preparing a binary solution. What do you mean by binary solution? Which is made up of two components. Now let us say we are preparing the solution by mixing component 1 and component 2. For our reference, we will take this as solute for all our future discussions. This is taken as a solute which is said to be non-volatile. Which is said to be non-volatile. Which is said to be non-volatile. And this is component 1. We always take it as volatile solvent. We always take it as volatile solvent for all our discussions. After assuming these things, then we have said that we have prepared a solution by taking two components. Let us say this is component 1 plus 2. Solution is made up of component 1 plus 2. It is made up of components 1 and 2. Then we said that since component 2 is said to be a non-volatile solute, since it is said to be a non-volatile solute, it will not exert any sort of vapor pressure. Above this, whatever vapors are there, we call it as P1. And vapor pressure of pure solvent, we take it as P1 naught. By adding a non-volatile electrolyte, by adding a non-electrolyte, by adding a non-volatile solute, to, by adding a non-volatile electrolyte solute to solvent 1, vapor pressure over the solution, decreases. Vapor pressure over the solution decreases. So that changes in the vapor pressure over the solution, we shall call it as delta P1, and that delta P1 should be equal to P1 naught minus P1. Delta P1 is the changes in the vapor pressure over the solution, and P1 naught is said to be the vapor pressure of pure solvent, and P1 is said to be the vapor pressure over the solution. Now, from Raoult's law, we know that P1 is equal to P1 naught x1. Now, let me call this as equation 1. Let me call this as equation number 2. Now, substituting the value of 2, substitute 2 in 1. Now, substituting the value, we can write this as delta P1. This is equal to, what is P1 naught? We'll write as P1 naught minus, what is P1? Substitute from equation 2. This is P1 naught x1. Now, delta P1 should be equal to, let me take P1 naught as common, multiplied by 1 minus x1, which will imply, this is what we have studied in the last class, delta P1 should be equal to P1 naught. Now tell me students, if a solution is made up of only two components, then the sum of mole fraction of all the components should be equal to how much? X1 plus x2 should be equal to how much? 1. So now tell me what is 1 minus x1? It should be equal to X2. Then after this we have studied about what we are going to do in the next part. I will write it here. Let me write here. What is delta P1? We have written it in equation 1 as P1 naught minus P1. I will write as P1 naught minus P1. That should be equal to, what have we written here? P1 naught into X2. Let me write as P1 naught into X2. Now bringing this to the denominator, we can write this as P1 naught minus P1 divided by P1 naught. This should be equal to X2. And now we say that what is P1 naught? Vapor pressure of the pure solvent. What is P1? Vapor pressure over the solution after dissolving non-volatile, non-electrolyte solute in the solution. And what is P1 naught? Vapor pressure of the pure solution. This ratio, whatever we have on the left hand side of this equation, we call this as RLVP. What is this called as? RLVP, relative lowering of vapor pressure. Now students, define what is relative lowering of vapor pressure. Relative lowering of vapor pressure is defined as the lowering of, it is defined as the ratio of lowering of vapor pressure to the vapor pressure of the pure solvent, or changes in the vapor pressure of the solution to the vapor pressure of the pure solvent, and this ratio is called as RLVP, and that should be equal to mole fraction of the component 2 in the solution, that is nothing but solute. Now we can replace X2 in terms of moles. P1 naught minus P1 divided by P1 naught, that should be equal to mole fraction of component 2 should be equal to number of moles of that component divided by total number of moles present in the solution, that is N1 plus N2. I told you that this is a formula. Further modifications can be done for this. Now if we assume that the solution that we have prepared is a very dilute solution, suppose if the solution is very dilute, if solution is very dilute, if solution is very dilute, what is the meaning of a dilute solution? The solution is very dilute. What is the meaning of a dilute solution? Dilute solution implies that the solute that we have dissolved is very less, that is number of moles of solute is very much less compared to the number of moles of solvent. If N2 is very much less than N1, this is applicable only for very dilute solutions. Then in the previous equation what we got, N2 divided by N1 plus N2, P1 naught minus P1 by P1 naught, that is equal to N2 divided by N1 plus N2. We can say that N1 plus N2 can be approximately nearly equal to N1 because N2 is very much less than N1. Substituting this in the above equation, this equation what we have studied, we can write P1 naught minus P1 divided by P1 naught. This should be equal to N2 divided by N1. Now let us say that we have prepared a solution by dissolving W2 grams of solute, W2 grams of solute in W1 grams of solvent, W1 grams of solvent, where M2 and M1 are molar masses, M2 and M1 are molar masses, molar masses of component 2 and 1 respectively, 2 and 1 respectively, 2 and 1 respectively. Now we can alter the equation what we have written, P1 naught minus P1 by P1 naught. Number of moles can be represented in terms of mass, and we can write that equation as P1 naught minus P1 divided by P1 naught, that should be equal to number of moles of component 2 should be equal to W2 divided by M2 divided by N1 is nothing but W1 divided by M1. Ultimately, we have to remember this equation, P1 naught minus P1 divided by P1 naught, that is equal to W2 into M1 divided by M2 into W1. Very, very important equation. As I told you in the last class, this is applicable only for dilute solutions. So unless you remember this formula, you cannot solve the problems on this. Problems on this formula is important for 3 marks. Problems on this formula is important for 3 marks. It is important for 3 marks. Usually one of the colligative property would be asked, so this also can be asked for 3 marks. You need to remember this formula, which is extremely important for your boards. Unless you remember this formula, you cannot solve any sort of problems. So this I have done in my last class. These derivations are done. Now we have to start solving the problems based on this. I told you to by heart this formula and come. Let us see, students, few problems which is given in your study material. Let us look into some problems. You don't have to write the problems, students. So it is already given in your study material. I'll tell you the page number, just you have to start solving those problems. It is given in page number 87. These problems are given in the page number 87 of your study material. We have to start solving the problem, question number 8, which is given in your study material. Now let us start reading this question now. Question is given as vapor pressure of pure benzene, vapor pressure of pure benzene at 30 degrees Celsius is 16.2 kilopascal. Tell me, students, what is the symbol that we are using for the vapor pressure of pure solvent? P1 naught. This is given as 16.2 kilopascal. 16.2 kilopascal. A solution containing 15 grams of non-volatile solute. So what is this 15 gram? 15 gram corresponds to solute. What is the mass of solute that we have represented? W2, which is dissolved in 250 grams of benzene. Benzene is what? Solvent. So therefore, what is this 250 grams? That is the mass of solvent. This 250 gram is the mass of solvent. Has a vapor pressure of 16.02. So what is this? They have given P1. It is 16.02 kilopascal. You can see by adding a non-volatile electrolyte, vapor pressure of the solution has decreased with respect to the pure solvent. Calculate the molecular mass. Calculate the molecular mass of the solute. Let us calculate the molar mass. M2 is a question mark. M2 is said to be a question mark. Tell me, students, what is the formula that we have to use for RLVP? This problem is connected to RLVP. P1 naught minus P1 divided by P1 naught, that is equal to W2 into M1 divided by M2 into W1. Now we know this is the standard formula that we have derived. Now see, W2 data is given, P1 naught data is given, P1 data is also given, this P1 naught is known, M1 molar mass, so we need to know what is M1. M1 is nothing but the molar mass of benzene. So benzene, what is the molar mass? 12 multiplied by 6 plus 6. This is equal to 78 gram per mole. 78 gram per mole. this is known. W1 has to be known, that is already given. So therefore we have to calculate what? M2. Let us first substitute. For writing the formula usually you will get 1 mark. Now substituting all the values here, what is P1 naught? It is 16.2 minus what is P1? 16.02 divided by what is P1 naught? P1 naught is said to be 16.2, that is equal to what is W2? 15 grams multiplied by what is said to be M1. So it is calculated to be 78. It is determined by knowing it as benzene, divided by M2 has to be calculated, multiplied by W1 value is known, that is 250. Now you have to solve for this using calculator, you can solve it. So implies M2, that will be equal to 15 into 78, 15 into 78 divided by 250. We have to bring it here, 16.2 minus 16.02, and this 16.2 has to be taken above. So take your calculator, students, solve for this. Take your calculator and solve for this. Tell me what is the answer. Tell me what is the answer, students. What answer do you get? Answer comes out to be 421.2 gram per mole. What is the answer? 400 and M2 will be equal to 421.2 gram per mole. Is it clear, students? One problem of this kind would definitely come, which is very important for the annual examination. Let us look into the next question. You don't have to write the question, it is given in your study material, which is there in page number 87, problem number 9. Read the question. Calculate the mass of a non-volatile solute. Calculate the mass of a non-volatile solute of molecular mass 40. You have to calculate what is W2. Calculate the mass of non-volatile solute W2, whose molar mass is given as 40 gram per mole. We need to know the unit of molar mass is gram per mole, which should be dissolved in 114 grams of octane. So solvent is octane, so W1 is equal to 114 grams. What is the formula of octane, students? Oct corresponds to 8, C8, since it is ane, it should be an alkane. It should be 2 into 8 plus 2, 16 plus 2 is 18, C8H18. You can calculate the molar mass of this. So 12 into 8, 12 multiplied by 8 plus 18. So this comes out to be 114 gram per mole. 114 gram per mole. Molar mass is also 114 gram per mole. So M1 is also known, that is equal to 114 gram per mole by knowing the formula of octane. To decrease the vapor pressure to 80%. So they are telling that in terms of percentage, let us say P1 naught is 100, then what will be P1? It has to be reduced to 80%, means P1 is 80. Now we have to calculate what is W2. Definitely we know what is the formula for RLVP. Formula for RLVP is P1 naught minus P1 divided by P1 naught, that is equal to W2 into M1 divided by m2 into W1. Substitute all the values, students. If you substitute the values, it is 100 minus 80 divided by 100. This is equal to W2 value has to be determined, W2 multiplied by M1 is known, that is 40. M1, sorry, it is not 40, 114 divided by M2, M2 is known, it is 40, multiplied by W1, W1 is known, that is 114. So this 114 cancels, implies W2 will be equal to 100 minus 8 is 20, 20 multiplied by 40 divided by 100. So you can calculate it easily. 20 ones are 25s are 5 ones are 5 8s are. So therefore, what is the mass of solute that has to be dissolved? So as to decrease the vapor pressure to 80%, it should be equal to 8 grams. It should be equal to 8 grams. Just note down the solution, students. Okay, let us go into the next question. So answer for this is 8 grams. Let us go for the next question, students. Question number 10. Question number 10. Read the question. The vapor pressure of pure water at 298 Kelvin is 23.5 millimeters of mercury. What is this 23.5? 23.5 millimeter of mercury is nothing but equal to vapor pressure of pure water. Water is usually used as a solvent, so this should be P1 naught. Calculate both vapor pressure and relative lowering of vapor pressure. Means they are asking what is P1? That is a question mark. Relative lowering of vapor pressure is nothing but P1 naught minus P1 divided by P1 naught, that is equal to question mark. Relative lowering of vapor pressure of an aqueous solution containing 50 grams of urea. So W2 is equal to 50. You know what is the formula of urea? Formula of urea is NH2 CO NH2. You can calculate the molar mass of this. 2 nitrogen atoms, that is 14 multiplied by 2, plus you have 1 carbon, that is 12, plus you have 1 oxygen, that is 16, plus what you have is 4 hydrogens, that is 4. 28 plus 12 plus 16 plus 4 is 20. So 20 plus 12 is said to be 32. 32 plus 28 is said to be 60 gram per mole. 60 gram per mole. So you know that what is the molar mass of solute? That is equal to 60 gram per mole. Now you know that what is the formula for relative lowering of vapor pressure? Formula for relative lowering of vapor pressure is P1 naught minus P1 divided by P1 naught, that is equal to W2 into M1 divided by M2 into W1. Let us keep on substituting all the things. We know what is P1 naught, that is 23.5, minus we need to calculate what is this P1. Let me write it as P1 divided by P1 naught is 23.5. This is equal to W2 is known, that is 50, multiplied by M1 has to be known. What is the molar mass of water? That should be equal to 18 gram per mole. 18 gram per mole. So let me substitute here, that is 18 divided by what is M2. M2 value is known, M2 is equal to 60 multiplied by what is W1. So already it is given, W1 is nothing but equal to 50. This is nothing but W1, sorry, this is W1, 850 grams of water, that is 850. Solve this using calculator, students. Tell me what is the value of P1. now you can calculate the value of P1. This is coming out as 23.086 millimeter mercury. Use calculator and solve it, students. Answer comes out to be 23.086 millimeters of mercury. Second part, what they have asked is that calculate the relative lowering. This is called as relative lowering of vapor pressure, RLVP. So if I calculate what is the value of this, that should be equal to RLVP. So therefore P1 naught minus P1 divided by P1 naught, that should be equal to 50 multiplied by 18 divided by 60 multiplied by 850. This will come out as 0.0176. So this is not having any unit. So this is all about question number 10, which is given in your material. Just note down the solution, students. Shall we go for the next question? Note it down. Okay, question number 11. Question number 11. You don't have to write this question, it is already given in your study material. So this is the last problem that we are studying now for RLVP. Okay, now read this. The vapor pressure of ether of molar mass 74 is 60 kilopascal. So since it is a pure substance, whatever they are given is P1 naught. P1 naught is equal to 60 kilopascal. And also they said that molar mass of it, so since it is used as a solvent here, it should be taken as M1, that should be equal to 74 gram per mole. If 3 grams of a compound A, so they are saying that what is the weight of solute, W2 is equal to 3 grams, is dissolved in 50 gram of ether, so W1 is given as 50 gram. You can see here, this is 3, this is for W2, W1 is 50, this is 74 M1. The vapor pressure falls to 56.8, means they are telling that what is P1? P1 is decreased to 56.8 kilopascal. Calculate the molecular mass of A. What they are telling is what is M2. M2 is a question mark. Okay, now we will write the formula for relative lowering of vapor pressure, then we shall start working out. So P1 naught minus P1 divided by P1 naught, that is equal to W2 into M1 divided by M2 into W1. Now let us start substituting all the values. P1 naught is known, that is 60, minus P1 naught is known, that is 56.8, divided by P1 naught is 60. This is equal to W2 value is known, W2 is 3 grams, multiplied by M1 is known, M1 is 74, it is given, divided by M2 has to be calculated, multiplied by W1 value is known as 50. You have to solve for this. So you will get the value of M2, implies M2 will be equal to 3 into 78 divided by this 60 can be taken above into 60 divided by 60 minus 56.8. 60 minus 57 is 3 and 2 is remaining, it is 3.2 into this 50. Solve this using calculator, students. M2 are going to get it as 83.25, 83.25 gram per mole, 83.25 gram per mole. Okay. Now we shall write a statement, then we shall proceed ahead later. Okay students, now there is a concept called as Raoult's law of Raoult's law Raoult's law of relative lowering of vapor pressure, RLVP. This definition is not given in your NCERT, but it is given in your material. So whenever a question on Raoult's law is asked, you have to read whether simply they have given state Raoult's law for a solution of volatile liquids, or simply Raoult's law, or they have given Raoult's law of relative lowering of vapor pressure. Whatever we said, that is P1 naught minus P1 divided by P1 naught, that is equal to X2. This is called as Raoult's law of relative lowering of vapor pressure. Whatever we have written P1 is equal to P1 naught X1, this is simply called as Raoult's law. This is simply called as Raoult's law. In your examination, you have to see whether you have to define this mathematical statement or you have to define this. Tell me students, what is the statement of relative lowering of vapor pressure? So that we have studied in the previous class. Relative lowering of vapor pressure. What is the statement for that, students? What you have studied in your last class, I told you it is important for 2 marks or 1 mark it can be asked. For a solution of volatile liquids, this Raoult's law statement, for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction in the solution. That is a statement of Raoult's law. Now what you are studying is Raoult's law of relative lowering of vapor pressure. Just go for your study material, page number 86, you can see relative lowering of vapor pressure, Raoult's law of relative lowering of vapor pressure. See students, that can also be asked for 1 mark. Just read the definition. Relative lowering of vapor pressure produced by dissolving a non-volatile solute in a solvent is equal to the mole fraction, of the solute in the solution. P1 naught minus P1 by P1 naught is equal to X2. If you tell this in the form of a statement, then we call it as Raoult's law of relative lowering of vapor pressure. Repeat the statement students. You see in page number 86 of your study material, relative lowering of vapor pressure produced by dissolving a non-volatile solute in a solvent is equal to the mole fraction of the solute in the solution. This can also be asked for 1 mark. Remember students, whenever there is a question on Raoult's law, you have to see whether they have mentioned simply Raoult's law or Raoult's law of relative lowering of vapor pressure. So 99.9% times this question is asked. Statement, what you have studied in the previous class. What is the statement of this? For a solution of volatile liquids, vapor pressure of each component of the solution is directly proportional to its mole fraction in the solution, present in the solution. So many times this is asked, but this statement is also given in your study material, so please do refer that. Now we have to study the next concept, that is elevation in boiling point. Let me erase this part. Elevation in a beautiful nice concept that we can study now. Relative lowering of vapor pressure is over. Now what we are studying is elevation in boiling point. Elevation in boiling point. The symbolic notation for this is delta TB. The symbolic notation that we use is delta TB. Delta means difference, TB is the boiling point. So now if we want to study about why there is elevation, elevation means what? Increase. Why there would be increase in the boiling point upon adding a non-volatile solute. Why there will be increase in the boiling point? Why there will be increase in the boiling point upon adding non-volatile solute to volatile solvent. If you know the concept, then studying this part will be very easy. Now let us consider, as I said you, 1 always stands for solvent which is volatile, 2 always stands for solute. This is non-volatile. This is said to be volatile. So these are the 2 points that you need to remember. What does 1 stands for? What does 2 stands for? Tell me, what does 1 stands for? Solvent. 2 stands for solute. Always remember, for all our discussions, solvent is volatile and solute is non-volatile hereafter. Even in RLVP also it will you to remember the same. Okay, now let me say that a solution is made by taking 2 components, as we said. So let us say this is component 1. Now let me say that we are adding component 2. Let me say that this is component 2, which is uniformly distributed in the solution. Now let me say that this beaker is said to be closed. You know that liquid has the tendency to undergo evaporation. So therefore, let me say that this black dots are said to be the vapors of component 1. Because of adding non-volatile electrolyte 2, this red dot corresponds to component 2, which is said to be non-volatile, which will not evaporate. Because of the presence of this non-volatile electrolyte, which is going to block the surface of the liquid, where it blocks, it will not allow the liquid molecules, that is component 1 molecules, to evaporate. Here it can evaporate, here it can evaporate, here it can evaporate, here also it can evaporate, but wherever red dot is present, it will block the evaporation of the liquid. Eventually, because of the blocking of the surface of the liquid molecules, what will happen to the vapor pressure upon adding non-volatile electrolyte? Vapor pressure after adding component 2, will it increase or decrease? It has to decrease. Vapor pressure decreases. Why does it decreases? Because solute molecule is going to cover the surface of a liquid. Where it has been covered, it is not allowing it to evaporate. It blocks the surface of a liquid. So vapor pressure decreases. In our last class, we have studied that vapor pressure is inversely proportional to boiling point, which implies boiling point is inversely proportional to vapor pressure. If vapor pressure decreases, what should happen to the boiling point? It will increase. So definitely, students, you have to remember, by adding a non-volatile solute 2 to the volatile solvent 1, vapor pressure of the liquid is decreasing. Because of the decrease in the vapor pressure, boiling point is increasing. Okay, now let us go for the part what we have to understand here. When you start adding more and more amount of component 2, when more solute is added, is added, what will happen to the blocking on the surface of a liquid? Blocking on the surface of a liquid by this red dot would increase because you are adding more amount of solute, that is component 2. If more blocking happens, so what will happen to the vapor pressure? Vapor pressure decreases more. If pressure decreases more, what would happen to the boiling point? It would increase. This is the basis. This is the theory that you need to remember now. Okay, now let us say that this delta TB means what? This is nothing but equal to boiling point of the pure solvent minus boiling point of the solution. Delta TB is what? Boiling point of solvent, pure solvent, boiling point of pure solvent, boiling point of pure solvent, boiling point of pure solvent. And what is TB standing for? Boiling point of solution. Boiling point of solution. Now let us see, delta TB depends on what? It is experimentally determined that this delta TB depends on the molality of the solution. This delta TB is directly proportional to the molality of the solution. You know that what is molality? You have studied in the first part of this chapter. Molality is nothing but number of moles of solute divided by volume of the solution, mass of the solvent, mass of solvent, mass of solvent in kg, mass of solvent in kg. So now, if delta TB, this is experimentally found, if molality is more, number of moles is more. Number of moles is more, blocking of the surface is more. So now delta TB should be equal to what? Delta TB should be equal to some constant. Let me call this as Kb into m. So now this Kb is called as molal elevation boiling point constant, or it is also called as ebullioscopic, ebullioscopic, ebullioscopic constant. It is also called as ebullioscopic constant. What is the symbol for that? Kb. Now tell me, students, what is the definition for Kb? Definition of Kb. Definition of Kb. What is Kb? Molar elevation boiling point constant. If the elevation in the boiling point is 1 or it can be equal to Kb when the molality of the solution is equal to 1. So now tell me, what is said to be the definition of Kb? Ebullioscopic constant is defined as the elevation in the boiling point of the solution when molality of the solution is 1. So if molality is equal to 1 implies delta TB is equal to Kb. So definition, molar elevation boiling point constant is the elevation in the boiling point when molality of the solution is 1, or when 1 mole of solute is dissolved in 1 kg of solvent. It is defined as elevation in the boiling point. It is defined as elevation in the boiling point, of the solution when the molality of the solution when the molality of the solution is unity or 1, or when 1 mole of solute is dissolved in 1 kg of solvent. This definition can be asked for 1 mark. Definition of Kb. It is defined as the elevation in the boiling point of the solution when molality of the solution is unity, or when 1 mole of solute is dissolved in 1 kg of solvent. Okay, now let us go for the little bit expanded form of this. Now tell me, students, what is molality? So this delta Tb will be equal to Kb multiplied by, what is molality? Number of moles of solute divided by mass of solvent in kg, mass of solvent in kilograms. What does N2 stands for? Number of moles of solute. Now let us say that for preparing the solution we have used W2 gram of solute in W1 grams of solvent. It was dissolved in W1 grams of solvent whose molar masses were M2 and M1, whose molar masses were M2. M2 gram per mole is the molar mass, of solute. Now let us do these substitutions here. Delta Tb should be equal to Kb. Kb is what? Molar elevation boiling point constant multiplied by what is N2? N2 is nothing but mass of the solute dissolved, that is W2 grams, divided by molar mass of the solute particles, that is M2, multiplied by, in the denominator, mass of the solvent in kg. We know that W1 grams of the solvent was used to dissolve W2 grams of solute, but this is in grams. To convert into kg, you have to divide by 1000. That 1000 goes to the numerator. So now tell me, students, what is delta Tb? Delta Tb is equal to Kb multiplied by W2 into 1000 divided by M2 into W1. Now let us see what is the unit for Kb. What is the unit for Kb? Let us see what is the unit for Kb. We know that delta unit for, what we have to study now is the unit for Kb. Unit for Kb. We know that delta Tb is equal to Kb into M, which implies Kb is equal to delta Tb divided by M. You know what is the unit of delta Tb? Changes in the boiling point, the unit should be Kelvin. Unit of boiling point, that is nothing but temperature, that is Kelvin, divided by, what is the molality? Number of moles divided by mass of the solvent in kg. Mass of solvent in kg. So that should be equal to K divided by, what is the unit for this? Mole divided by mass is there, unit of that is kg. So implied, what is the unit for that? Kelvin kg per mole. Kelvin kg per mole. It is important. Unit of Kb is asked in the annual examination. So very, very important for 1 mark. It can be asked for 1 mark. What is the SI unit for Kb? What is the SI unit of Kb? Kelvin kg per mole. Take it as a question, mark it. It is very important. This formula you need to by heart, students. You need to remember this formula. You need to know what is the unit of Kb, that is equal to Kelvin kg per mole. Now we have to look into the graph. let us see that we are plotting the graph of vapor pressure versus temperature. We are plotting the graph of vapor pressure. As you move above, vapor pressure increases versus temperature. As we move from left to right, temperature increases. Tell me, students, as we keep on increasing the temperature, what will happen to the vapor pressure? When the temperature increases, kinetic energy of the molecules increases, escaping tendency increases, vapor pressure keeps on increasing. So let me say that vapor pressure keeps on increasing. Vapor pressure keeps on increasing. This is experimentally obtained graph. So let us write it like this. It keeps on increasing. It increases. Okay. Now, this is for solvent. Let us see what we are writing here. This is for a solvent. This is for a solvent. This is for solvent. Okay. Now tell me, what is boiling point? What is the definition of boiling point? The temperature at which the vapor pressure of its own liquid is equal to 1 bar pressure. Let me say this particular pressure is said to be 1 bar. This is said to be 1 bar. So let me say that this is the dotted line which I represented as a 1 bar. This particular temperature, let me say this particular temperature is called as boiling point of the pure solvent. I should write it as TB naught. This is called as boiling point of the pure solvent. So TB naught already we have seen. This is nothing but equal to boiling point of pure solvent. 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 Now, students, what would be the vapor pressure of the solution with respect to the solvent at any particular temperature? Vapor pressure would be more or less. Upon adding non-volatile solute, blocking of the surface would increase, vapor molecules would decrease. Definitely at any particular temperature, vapor pressure of the solution is less than that of pure solvent. So now whatever I draw in the blue line, so let me say that this is the variation of vapor pressure. This would be the variation of vapor pressure of the solution. This is for a solution. This is for a solution. So let me write it here. This would be the vapor pressure curve for a solution. Now wherever the curve meets, here the vapor pressure of the solution would be equal to 1 bar. So now let me say that, let me draw the line below. So this particular temperature, what we get, that is called as the boiling point of the solution. Let me call it as, this is called as the boiling point of the solution. Let me write it as TB. What does TB stands for? Boiling point of the solution. TB is boiling point of solution. This is called as boiling point of solution. Now you can see there is an increase in the boiling point. So you can see it here. The increase in the boiling point is here. Let me say the increase, this is called as delta TB. What is it called as? Delta TB, difference in the boiling point. That is called as what? Delta TB. Now tell me, students, what is delta TB? Final pressure, so that is TB minus TB naught. That is called as the changes in the boiling point. So definitely boiling point of the solution is more, boiling point of the solvent is less. That is why we have given the heading as elevation in the boiling point. That is why we have given point as elevation in boiling point. This formula is very important, students. Delta TB is equal to Kb into W2 into 1000 divided by M2 into W1. 2 always stands for solute, 1 always stands for solvent. Capital letter M is for molar mass, small letter W is for the mass of the substance. Is it clear, students? Note down this formula. Now, usually the value of Kb would be given in the question paper, but Kb of water, you need to remember it. It is better to remember 0.52. Unit already we have discussed. What is the unit? Kelvin kg per mole. Kelvin kg per mole. So this value you need to remember. Kb is equal to 0.52 Kelvin kg per mole for water. For problem solving, you need to know this. Usually it will be given in the question paper. If not given for water also, you need to remember this value. Okay, shall we go for the numerical part of this, students? What is the formula for delta TB? You have two formula. Delta TB is equal to TB minus TB naught, and another formula is that delta TB is equal to Kb into W2 into 1000 divided by M2 into W1. So we should know that delta TB is directly proportional to molality of the solution. Why it is directly? Molality is more, number of mole is more, number of moles is more, blocking of the surface is more, blocking of the surface is more, vapor pressure decreases, boiling point increases. Let us start solving the problems on this now. You don't have to write the problem, students. It is there in your study material. Problem number 12. It is given in page number 88. It is given in page number 88. Start reading, students, now. Boiling point of water at 750 millimeter of mercury. Boiling point of water at 750 millimeter of mercury is 99.63 degrees Celsius. How much of sucrose is to be added to 500 grams of water such that it boils at 100 degree Celsius? Now, boiling point of water at 750 milliliter of mercury is 99.63, means that nothing is added for that. So whatever they have given is TB naught, boiling point of pure water. This is equal to 99.63 degree Celsius. Usually we need to convert this into the Kelvin scale, but since we want to find the difference, we don't have to worry about whether it is in the degree Celsius or in the Kelvin scale. So how do you convert this into Kelvin scale? 273.15 plus 99.63. So this comes out to be, calculated, students, 273.15 plus 99.63. So this will be equal to 372.78 Kelvin. And they have given boiling point of the solution should be 100 degrees Celsius. 100 degrees Celsius. This would be equal to 373.15 Kelvin. Then they said sucrose, W2, how much has to be added? But we should know what is the molar mass of sucrose. What is the formula of sucrose? C12H22O11. So this should be equal to 12 multiplied by 12 plus 22 multiplied by 1 plus 11 multiplied by 16. So add this, what you get will be 342 gram per mole. So we know what is M2, that is equal to 342 gram per mole. Then they have given it is dissolved in 500 grams of water, that is solvent. W1 is equal to 500 grams. So we know the formula delta TB is equal to Kb multiplied by W2 multiplied by 1000 divided by M2 into W1. We need to calculate delta TB. We know what is the formula to calculate delta TB. Delta TB, that will be equal to TB minus TB naught. Substituting the value of TB as, you can take the difference of 100 minus 99.63, or you can take the difference of 373.15 minus 372.78. The value remains to be the same. So you can calculate what is the difference delta TB. Delta TB, this comes out to be 0.37. Let us see, 373, use the calculator, 373.15 minus 372.78. This is equal to 0.37. So substitute all these values here. So we know that what is delta TB, 0.37, that is equal to, we know what is Kb. Kb for water is not given, we should know already. I told you that you have to remember. So what is the value of Kb? We need to remember this. I told you if it is not given in the problem, you have to remember Kb for water is equal to 0.52 Kelvin kg per mole. You need to remember this value. So that is 0.52 multiplied by W2 is asked, multiplied by 1000 divided by M2 is known, that is 342 multiplied by W1 is 500, implies W2 will be equal to 0.37 multiplied by 342 multiplied by 500 divided by 0.52 multiplied by 1000. Solve this and tell me, students, what is the answer for this? Implies W2 will be equal to 121.67 grams. 67 grams. Note down the answer, students. We'll go for the next question. Shall we go for the next question? Question number 13. Question number 13. Eighteen grams of glucose. So W2 is given. W2 is equal to 18 grams is dissolved in 1 kg of water. So water is a solvent. W1 is equal to 1 kg, that is equal to 1000 grams. That is equal to 1000 grams. Because in our formula what we have assumed is that all in grams, masses which are dissolved is in grams. At what temperature the solution will boil? TB is asked. TB is a question mark. Under 1.013 bar, this is nothing but equal to 180 m. At 1 atmospheric pressure, boiling point of water, that is TB naught, is equal to 100 degrees Celsius. This is known from your high school. You have studied standard normal boiling point of water is 100 degrees Celsius. This is equal to 373.15 Kelvin. And they have given Kb for water. In this problem, they have given Kb is given as 0.52 Kelvin kg per mole. Kelvin, kg per mole. Now we need to calculate TB. First we shall calculate delta TB. Delta TB is question mark. If we calculate delta TB, then we know delta TB is equal to TB, boiling point of the solution, minus boiling point of the pure solvent. So first we shall calculate delta TB, then we shall calculate what is TB using this formula. Now, as usual, the formula that we have used, that is delta TB is equal to Kb multiplied by W2 into 1000 divided by M2 into W1. So delta TB we shall calculate first. Delta TB, that will be equal to Kb is known as 0.52 multiplied by W2 is known. W2 is equal to 18 into 1000 divided by molar mass of solvent has to be known, M2. M2, since it is water, it is 18 gram per mole. 18 gram per mole, let me write as 18, multiplied by W1 is known, that is 1000. That is 1000. Now easily you can determine what is the value of delta TB. 18 cancels, 1000 cancels, implies delta TB is equal to 0.52 Kelvin. We know that delta TB is equal to TB minus TB naught. So this is 0.52, that is equal to TB has to be calculated, minus TB naught is known. TB naught is 373.15, implies TB will be equal to 373.15 plus 0.52. So therefore you can calculate the value of TB, that will be equal to 373.202. That will be equal to 0. Students, we have taken 18 gram of glucose. This is 180, sorry, this is said to be 180, not 18, since it is glucose. This should be 180, so this will be equal to 10. This will be equal to divide by 10, so this will be equal to 0.052. So this is 0.052 and this will be equal to 373.202 Kelvin. Just make a correction, students. This will be 180, not 18, 180 gram per mole. So I have to change this as 180, 18 ones are, this is 10 times. So 0.52 by 10, this will be equal to 0.052 Kelvin. Substituting here, so you'll get it as 373.202, because glucose has a molar mass of, glucose formula you know, C6H12O6. This will be equal to 12 6 are 72 plus 12 plus 15 into 6, 16 into 6, it is 96. This is coming out as 180 gram per mole. This is equal to M2. Substitute these values, you'll get the answer as 373.3202 Kelvin. Note down the solution, students. Let us look into one more problem. Okay. Boiling point of solution containing 0.105 gram of a non-volatile solute in 15.84 gram of ether was found to be 0.1 degree Celsius higher than that boiling point of the pure ether. What is the molecular mass of solute? Okay, now let us start writing the given things. given things are boiling point of a solution containing 0.105 gram of a non-volatile solute. So W2 in 15.84 gram of solvent, that is W1, that is ether. Then they are telling that delta TB higher by means delta TB is given as 0.1 degree Celsius, difference remains same, or 0.1 Kelvin, they are one and the same. What is the molecular mass of the solute? M2 is a question mark. Kb for ether is given, Kb is equal to 2.02 Kelvin kg per mole, Kelvin kg per mole. Students, already many times you have solved the problem, only the parameters are different here. So here you have to calculate M2. First write the formula, standard formula, delta TB is equal to Kb into W2 multiplied by 1000 divided by M2 into W1, implies M2 will be equal to Kb multiplied by W2 multiplied by 1000 divided by delta TB into W1. Substituting all the values, you can calculate the molecular weight of the solute. Kb is given as 2.02 into W2 is given as 0.105 grams into 1000 divided by M2, molar mass of the solute has to be calculated. Delta TB is given as 0.1 multiplied by W1 is given as 15.84. Solve this using calculator, students, you'll get the answer. A simple question. These kind of questions would be asked in the annual examination. So answer comes out to be 133.901 gram per mole. 901 gram per mole. gram per mole. Okay, shall we go for the next question, students? So numericals. So I have solved 3 problems based on elevation in boiling point. So we'll study the next concept, then we can go for the numericals of that. Okay, we shall study the next concept, students. The next concept that you are going to study is depression in freezing point. Depression in freezing point. Depression in freezing point of the solution. Depression in freezing point of solution. Depression in freezing point of the solution. So what all explanations I gave you for the previous one, how to prepare the solution. So we have studied that W2 grams of non-volatile solute, W2 grams of non-volatile solute was dissolved in W1 grams of volatile solvent so as to make a solution. So all these things you need to remember what we have discussed in the previous case. Now I'll explain you this in the form of graph. Now let us say that we are plotting the graph of temperature in Kelvin. Let us say that here it is the vapor pressure. As you move above, vapor pressure increases. Now let us say, student, at any particular temperature, you know how would be the vapor pressure curve for a solution. Since we are studying about freezing, we are decreasing temperature so as to convert a liquid into a solid. So initially when the temperature, let me say some Kelvin, here would be the vapor pressure. Slowly when you keep on decreasing the temperature, vapor pressure decreases since the kinetic energy of the molecule decreases, and at a particular temperature, let me say, it freezes, it becomes solid. Up to here it is for solvent, this is for a solvent, but this is in the liquid state. Once it freezes, it becomes to be a solid. After this particular temperature, let me say that there will be rapid decrease in the vapor pressure, because solids have less tendency to undergo evaporation. So this is also for a solvent, this is also for a solvent, this is also for a solvent, but this solvent is in the solid state. So we can call it as a frozen solvent. We can call this as a frozen solvent. So at a particular vapor pressure, so let me say that at this particular temperature, solution has started freezing. So this particular temperature is called as what, students? So this particular temperature should be called as TB. This should be called as TB, yes, sorry, TF, freezing point, TF not because it is a pure solvent. You know that at any particular temperature, what would be the vapor pressure of the solution? As you have discussed in the previous case, will it be above this curve or below this curve? At any particular temperature, what would be the vapor pressure of the solution with respect to the pure solvent? It is always less. So let me say that it is always less. It keeps on decreasing, and let me say that when it reaches this particular point, it becomes a solid. Then later it coincides with it. Later both of them are coinciding. So this is coinciding, both of them are coinciding. So now we can say that this particular point where it has been freezed, so we call this as, this particular temperature we can call it as TF. Now tell me, students, what has happened to the freezing point of the solution? This blue color line is for solution, this is for solution, variation of vapor pressure, the solution with respect to temperature. This is for the pure solvent. You know that for any solution, vapor pressure would be less than its solvent at any particular temperature. Now what has happened to the freezing point? You can see it has decreased, and this difference we call it as delta TF, and that should be equal to what? TF naught minus TF, and we call this as depression. Since there is decrease in the freezing point, we call it as depression in the freezing point of the solution. As we have studied in the previous case, delta TF is directly proportional to M. As we have seen in the previous case, delta TB is directly proportional to M. Here we say that delta TF is directly proportional to M, implies delta TF will be equal to some constant, I should call here as Kf into M, where M is the molality. Now we can substitute it as we have done in the previous case. Delta TF will be equal to Kf into number of moles of solute divided by mass of the solvent, let me call it as W1 in grams. So this is in grams, divided by 1000. So this is nothing but gram per mole. So therefore it will be converted into kg. Now still we can substitute delta TF will be equal to Kf multiplied by N2 can be written as W2 divided by M2, that is number of moles, into 1000 into this is W1. So you should know that just like in the previous case we had a constant called as abeloscopic constant or molar elevation boiling point constant, here also you will be having a constant which is known as molar depression freezing point constant. Now tell me, students, what does Kf stands for? Kf is equal to molar elevation, depression, since it is decreasing, molar depression freezing point constant. As we had a substitute name for molar elevation boiling point constant as abelioscopic constant. Here also you will be having an alternate name for this, which is called as cryoscopic constant, which is known as cryoscopic constant. It is also known as cryoscopic constant. It is also known as cryoscopic constant. CRYOSCOPIC, cryoscopic constant. Cryoscopic constant. Molar depression freezing point constant or cryoscopic constant. This graph is already given in your material, students. Now let us see what is the unit for Kf. What is the unit for Kf? As you have already written, delta Tf is equal to Kf into m, implies Kf will be equal to delta Tf by m. This is equal to delta Tf divided by molality is nothing but number of moles of solute divided by mass of solvent in kg. So this will be equal to, what is the unit of difference in temperature? Kelvin. Kelvin divided by number of moles. What is the unit? Number of moles is mol by mass of the solvent in kg. So divided by mass of the solvent in kg. So therefore, as we have seen in the previous case, Kf is also having the same unit as Kelvin kg per mole. Kelvin kg per mole. This unit can be asked for 1 mark. Important, students. This unit also can be asked for 1 mark. What is the SI unit of molar depression freezing point constant or cryoscopic constant? Now can you define what is Kf? Can you tell me what is the definition of Kf? As we have defined in the previous case, this should be equal to 1. So molar depression freezing point constant is the depression in the freezing point when molality of the solution is 1 molar. When molality of the solution is 1 molar. I am not writing the definition, students, since we have defined it in the previous case in the similar manner. So now tell me, students, what are the important formulas that you need to remember under this side heading, depression in freezing point? The important formulas that you need to remember is delta Tf is equal to Tf naught. Delta Tf is equal to, we know that freezing point of the solvent is more, minus Tf. Delta Tf is equal to what? Kb, not Kb, Kf multiplied by W2 into 1000 divided by M2 into W1. These are the two formulas that you need to remember. Then Kf for water, you need to remember this value. Kf for water is said to be 1.86 Kelvin kg per mole. Kelvin kg per mole. So these are few important things that you need to remember under depression in freezing point. Usually graphs are not asked, numericals based on these formulas would be asked. Okay, let us start solving the problems on this, students. I'll erase this. Read this problem, students. You don't have to write this problem. Once again, this problem is given in your study material. It is given in page number 89, question number 15. Dissolution of 0.643 gram of a non-volatile solute to 130 grams of benzene lowers the freezing point by 0.48 degrees Celsius. Calculate the molecular mass of the solute. Okay. Dissolution of 0.643 gram of non-volatile solute. So what is that 0.643? W2 is equal to 0.643 grams to 130 grams of benzene, means mass of solvent, that is W1, that will be equal to 130 grams, and they have given that lowers the freezing point by 0.48 degrees Celsius. So delta TF value is given. Delta TF is equal to 0.48 degrees Celsius. Difference remains the same, or this is equal to 0.48 Kelvin. Difference would remain same. Calculate the molecular mass of solute. M2 has to be calculated. Kf value is given, you can see. So Kf value is given as 5.12 Kelvin kg per mole. Kelvin kg per mole. Now students, you know what is the formula? Delta TF is equal to Kf multiplied by W2 multiplied by 1000 divided by M2 multiplied by W1. Let us rearrange this formula. Implies M2, that will be equal to Kf multiplied by W2 multiplied by 1000 divided by delta TF into W1. Substitute all the values. Implies M2 will be equal to Kf value is 5.12 multiplied by W2 value is given as 0.643 multiplied by 1000 divided by delta TF is 0.48 multiplied by W1 is 130. Take your calculator, students. Tell me what will be the final answer. M2 will be equal to how much? The final answer will come out as M2 will be equal to 52.76 gram per mole. 52.76 gram per mole. Okay, shall we go for the next question, students? Go for question number 16 in your study material, so which is there in page number 89. Read the question, students. Calculate the mass of ascorbic acid. Formula is given as C6H8O6 to be dissolved in 5 grams of acetic acid to lower the freezing point by 1.5 degree Celsius. Now, K for acetic acid is given. Calculate the mass of ascorbic acid, that is a solute. So, they are asking what is W2. W2 is a question, and they said the formula of that is said to be C6, H8 and O6. So 12 into 6 is 72 plus 8 plus 8 plus 16 into 6 plus 16 into 6. So you can calculate this molar mass. This comes out to be 176 gram per mole. 176 gram per mole. This is coming out to be 176 gram per mole. Is dissolved in 5 grams of acetic acid. W1 is equal to 5 gram. W1 is equal to 5 gram. freezing point is lowered, they said delta TF value is given, that is equal to 1.5 degrees Celsius, or it should be equal to 1.5 Kelvin. Difference remains the same. Kf value is equal to 3.9 Kelvin kg per mole. Kelvin kg per mole. Okay, now we know what is the formula for solving this. So we have solved already previous problem, similar kind of problem. It is delta TF is equal to Kf multiplied by W2 into 1000 divided by M2 into W1. Delta TF value is known, this is 1.5, this is equal to Kf, that is 3.9 multiplied by W2 value has to be calculated, multiplied by 1000 divided by M2 value is known as 176. We have determined it, we have calculated, multiplied by W1 value is given as 5 grams. It is given as 5 grams. Upon solving, you can get W2 will be equal to 1.5 into 176 into 5 divided by 3.9 into 1000. 3.9 into 1000. Calculated using calculator, students. W2 will be equal to 0.3385 grams. 0.3385 grams. Is it clear, students? Now let us go for the next concept. So we have finished the concept of depression in the freezing point. I'll give you a formula which based on that formula problems may not be asked, but still you need to know the formula since it is given in the NCERT. We have written what is Kb and what is Kf. How to determine the value of Kb or Kf? So we don't have to derive it, but we need to remember Kb is given by mTb square R divided by delta H of vaporization multiplied by 1000. Similarly, you need to remember for Kf, this is equal to mTf square R divided by delta H fusion multiplied by 1000. You need to remember the formulas which is given in your NCERT. Now you should know what is M. M is the molar mass of the solvent. What does M stands for? So M stands for the molar mass of the solvent. Molar mass of solvent. And remember here TB stands for boiling point of pure solvent. TF stands for freezing point of pure solvent. Delta H fusion, enthalpy of fusion, and delta H vaporization is nothing but it is the amount of energy which is required to vaporize 1 mole of a liquid into the respective gaseous state. I think this point is clear to you, students. So this formula you don't have to by heart it, but as a shortcut I'll tell you how to remember this. Can you tell me a company which provides you rasam powder and some sweets? MTR. So you can see the similarity here, MTR. So where we have a square here, MT square R. So MTB square R divided by, so always for vaporization, boiling means vaporization, freezing means it is fusion. So therefore you can remember this. So as a formula and as a shortcut, MTR. So Kb is equal to mTb square R divided by delta H vaporization into 1000 divided by 1000. Kf is equal to mTf square R divided by delta H fusion into 1000. So you can also use the notation m1 here, then this will be m1. So Tb, remember this is for pure solvent, that is important, and here Tf, this is also for the pure solvent. Okay, now let us go for the next colligative property. The next colligative property that we need to study is osmotic pressure. The next concept that we need to study is osmotic pressure. Osmotic pressure. The symbol used for this osmotic pressure is pi. The next concept that we need to study is osmotic pressure. Okay, now students, to understand the concept of osmotic pressure, so even though we don't want to study much about osmosis, but we need to know what is osmosis. We need to know a process known as osmosis. What is osmosis? To understand this concept, I would say you are taking pure solvent here. Let me say pure solvent is taken. This is said to be pure solvent. Let me say I am going to take a funnel. Let me call it as a Thesel funnel. So biology students might have seen this in your biology lab. You might have done this experiment. So let me take a Thesel funnel. You don't have to draw this, it is already there in your material, it is also there in your NCERT, and here we are tying it with a semi-permeable membrane. So let me say that this, whatever we have placed, this is said to be semi-permeable membrane. We have taken a semi-permeable membrane. Now we shall take some solution inside. We shall take some solution inside. This pink color is solution. We shall take some solution here. When you place this Thesel funnel in a pure solvent, generally you know that this solvent molecules will enter and dilute the solution, and eventually the level of the solution increases. The level of the solution here, it increases. That is because of the dilution of solution, it increases. See, this was the initial level, it has increased from here to here. So let me say the height to which it has been raised is called as h, and we said that height of a liquid column is nothing but equal to pressure, so we call this as pi, and this pi should be equal to h rho g, where rho is the density and h is said to be the height and g is said to be the acceleration due to gravity. Whatever height has been attained, that is the extra pressure that has been applied on this solution so that the liquid has been raised, and we call this extra pressure so as an osmotic pressure. If I apply an extra pressure from the above, then this process of osmosis would not happen. So now we say that this is solvent. Inside whatever we have placed, this is called as solution, and solution and solvent is separated by semi-permeable membrane. Certain important examples are given for semi-permeable membrane in your NCERT. So certain naturally occurring membranes are present, so which may be from animal source, or it can also be from the plant source. Animal source or plant source. So pig's bladder is an example for semi-permeable membrane. It can be asked. Pig's bladder is an example for semi-permeable membrane. Parchment paper is also an example for semi-permeable membrane. And another important synthetic semi-permeable membrane is given in your NCERT. This is cellophane. This is synthetic semi-permeable membrane. This can also be asked for 1 mark. Example for semi-permeable membrane can also be asked for 1 mark in your annual examination. So give an example for naturally occurring semi-permeable membrane. You can give the example of pig's bladder or parchment paper, or they may also ask you an example for synthetic semi-permeable membrane. You can give the example of cellophane. Some other examples for osmosis that you can also note is that, see, in order to prepare pickles, raw mango is placed in NaCl, You know that after some time, if this was the original size of the mango, let me say this is said to be mango, when you keep it in NaCl, maybe let me say after 6 months, what would happen to the size of the mango? Would it swell, or would it remain as such, or would it become small, would it shrink? You might have seen new home, it would shrink and it would get this shape. Why the mango's size has been shrinked? Why it has shrinked? Whatever water content was present inside mango, so that has come out so as to dilute NaCl, so as to melt NaCl. Initially when you have poured only salt, after 6 months you might have seen that has become a salt solution. The only reason is that whatever water is present inside the mango, it has come out, and hence that mango size would be shrinked, and that is because of osmosis. You might have seen another kind of example, dry grapes. If you put these dry grapes into water, for the next day the size of the dry grapes would be more, it would swell. It is because there would be sugar solution inside the grapes. When you put it into water, because of the high concentration of sugar inside, so water enters inside and it dilutes, and definitely what should happen to the size of the dry grapes? It has to increase. We call it as it swells. All these are examples for osmosis. So knowingly or unknowingly, this principle of osmosis is being used in our daily life. Some more examples you can see. If you have a flower, so suppose it should not if it should be remaining fresh, then we need to cut the bud of that flower, then we need to keep it in water so that it would be fresh, it would not shrink, or it would not lose its stiffness. Now let us come to the point of osmotic pressure. The required concept here is the osmotic pressure. Now let me say that we are having a compartment. So a big vessel is divided into 2 compartments. Let me say on to the one side we have pure solvent. This is said to be pure solvent, which is separated by semi-permeable membrane. Let me say that this particular thing is said to be semi-permeable membrane, SPML, right? Semi-permeable membrane. And on to the other side, let me say that we are having the solution. Let me say that this is said to be the solution. Let us say this is said to be the solution. Now tell me, students, when you have taken 2 liquids separately in 2 different compartments which are separated by semi-permeable membrane, and now a liquid has the tendency to undergo evaporations, definitely above the surface of a liquid there should be some pressure, so we should call it as vapor pressure. Let me call this as vapor pressure 1. Above the surface of the solution also there should be some vapors, and it should also exert some sort of vapors pressure, so let me call it as vapor pressure 2. Now can you tell me, students, if you compare the vapor pressure 1 and vapor pressure 2, which one would be of higher magnitude? Which one would be of higher magnitude? Let me say that this is liquid, pure solvent, above it has some vapors. This is solution, above that it has its own vapors, and it would be called as vapor pressure 1 and vapor pressure 2. If you compare the magnitudes of this vapor pressure, which would be the higher one? Since this is a solution which is made up of non-volatile solute dissolved in a volatile solvent, vapor pressure of this should be less. So, vapor pressure 2 would be less than vapor pressure 1, as we have discussed in the previous two cases. Whenever you say the vapor pressure on this is less, the vapor pressure on this above this solution is more, above this solvent is more, it exerts some sort of pressure. Since there is imbalance in the vapor pressures, in order to equalize it, some solvent molecules, because of the microporous small structures, so it allows only solvent molecules to move, solvent molecules start moving this side. So, what would happen to this? It gets diluted. When the solution gets diluted because of the movement of what? Solvent molecules through semi-permeable membrane, volatility of the solvent has to increase, because when the solution is diluted, number of solute particles covering per unit volume on the surface of this would be less, escaping tendency becomes more, and this process of osmosis would continue until the vapor pressure on the two sides becomes equal, until the vapor pressure here will be same. So, I think now you got what is the reason for osmosis. Now, if I don't want to see the movement of solvent molecules from pure solvent side to the solution side, then I need to apply an extra pressure. I need to apply an extra pressure here, so that this vapor pressure value and this vapor pressure value is same. So, if I apply an extra pressure, so that what is the magnitude of the lesser magnitude of the vapor pressure on the solution side, if I apply it using a piston, then if I make it as Vp2 is equal to Vp1, then since there is no difference in the vapor pressures, there would be no movement of this solvent molecules from solvent side to the solution side. And whatever extra pressure that you need to apply here, so as to just prevent the process of osmosis, that is called as osmotic pressure. So, we have to apply an extra pressure on which side? Onto the solution side. If you apply the extra pressure onto the solution side, so as to just prevent the process of osmosis, that is a movement of solvent molecules from pure solvent side into the solution side, we call that as osmotic pressure. So, what is the definition of osmotic pressure? The extra pressure that has to be applied on the solution side, so as to prevent the process of osmosis, is known as osmotic pressure. Now, instead of this, now if I take two solutions, let me say that you have a beaker which is converted into two compartments. Let me say this is said to be solution 1, this is said to be solution 2. Both are solutions, solution 1 and solution 2. Now, let me say that this side the concentration of the solution is C1, onto the other side on the other compartment the concentration of the solution is said to be C2. Now, for studying a different case, let me say that C1 is greater than C2. Now, it is very obvious that if the concentration is more on here side, vapor pressure is less here, vapor pressure is more. Here vapor pressure would be more. So, as to prevent the process of osmosis, definitely you know that here vapor pressure is less, here vapor pressure is more. So, from solution 2, the solvent molecules starts moving into the vapor pressure lesser side, that is from compartment 2 the solvent molecule starts moving into the compartment 1 until the vapor pressure becomes equal. Now, tell me students, if I want to prevent the process of osmosis, where should I apply the pressure? Here vapor pressure is more, here vapor pressure is less. Definitely I have to apply pressure on this side, I have to apply pi here. So the question can also be asked. Now can you tell me, if I connect this into pure solvent, if I connect into pure solvent in two different cases, so which one would be having the higher osmotic pressure? You should know that higher the concentration of the solution, higher would be the pressure. So pi is directly proportional to the molar concentration, and also it is dependent on temperature. So therefore you can say that pi is equal to some constant R into C into T. So therefore I can say pi is equal to remember, cathode ray tube is the shortcut. You can remember pi is equal to CRT. Now we should remember what is C. In all previous cases we have used molality, but here this C is concentration in molarity, concentration in molarity, concentration in molarity, where C is said to be concentration in molarity. So pi is directly proportional to the concentration of the solution in mole per liter, and pi is directly proportional to temperature. So it is very obvious that pi is equal to CRT. What is C? Concentration in molarity. What is molarity? Number of moles of solute divided by volume of the solution in liter into RT, implies pi is equal to, what is N2? Number of moles of solute. Let me write as W2 divided by M2. W2 is the weight of solute which has been used for preparing the solution, and M2 is said to be the mass, molar mass of the solute, into RT into V. Very, very important formula, students. To solve the problems, you need to remember this. Pi is equal to W2 into RT divided by M2 into V. I told you a shortcut to remember. Osmotic pressure, pi is equal to cathode ray tube. It is not actually cathode ray tube, it is a shortcut to remember. So C is the concentration in molarity, R is universal gas constant, T is temperature. The unit of R depends upon what is the unit of pi, or what is the unit of pi, that will decide what is the unit of R. So definitely if the concentration is expressed in molarity, it cannot be 8.314 because mole per liter. So if pi is expressed in bar, pi has to be expressed in bar, then R will be equal to 0.08314 bar liter per Kelvin per mole, per Kelvin per mole. So if R has to be expressed in terms of ATM, then R will be equal to 0.0821. It is ATM liter per Kelvin mole, per Kelvin mole. So we have to study a concept called as reverse osmosis. Let us study this in our next class, students. So please read all the concepts what I taught you. In order to solve the problems on this, you need to remember this formula. Pi is equal to W2 into RT divided by M2 into V, where W2 is the mass of solute dissolved, mass of solute dissolved, and M2 is the molar mass. M2 is the molar mass of solute, molar mass of solute. V is the volume of solution, volume of solution. Usually it is expressed in liters, volume of the solution in liters. Please note down all these things, students. Do refer your study material also. So fill in the blanks wherever empty space is given. In the next class, let us study something about reverse osmosis. Then we shall start solving the problems based on this. These are very, very important 4 colligative properties we have studied. RLVP, relative lowering of vapor pressure. Second one was elevation in boiling point, and third one was depression in freezing point, and the last one was osmotic pressure, where we have studied a concept of what is osmosis, then we have studied what is osmotic pressure, then we have studied the mathematical formula for pi. Pi is equal to W2 into RT divided by M2 into V. If you remember pi is equal to CRT, then all things can be memorized, where C is the concentration in mole per liter. Thank you, students. We shall see in the next class.